improving self-reported measures of innovation skills in an interdisciplinary undergraduate STEM course. So to give you a brief overview of this talk, what I want to begin with is what is this course, this interdisciplinary undergraduate STEM course? It's called Bioinspired Design, why we use it and why it's important. I want to then talk about the evaluation and assessment that we do in this course and how that connects to some of the things students are accomplishing in the course. And I want to conclude by thinking about design-based research and how we can use the information from the evaluation and assessment to inform improvements to the course and improvements to the assessment. So to begin, I ask this question: what is bioinspired design? It's sometimes called biomimicry, and I want to explain now what it is and why we use it, why it's a phenomenal way to look at an interdisciplinary course and have students do things in a STEM course. So here's how we sort of advertise to students. We show them the beauty of bioinspired design. It's an awesome, completely interdisciplinary field that is growing each and every day. It involves engineering, biology, physics, mathematics, you name it. And we actually try to emulate that same interdisciplinary nature by having this course open to all students, all years, all majors, no prerequisites. Importantly, students in this course are in interdisciplinary teams. They are matched with other non-majors, STEM majors, non-STEM majors, whatever it might be, and they're completing projects. They're making bio-inspired designs, sort of emulating the actual work being done in the field. Things that include bio-inspired design could be like a cockroach-inspired robot or a gecko-inspired adhesive that makes a better medical adhesive. All of this is sort of the process that we want students to engage in as they complete this course. So one of the things that students do that's critical in this course are what we call creative design labs. Students create inventions that have societal relevance. We want students to not only just make stuff, but make stuff that matters, make stuff that's societally important, and utilize nature to sort of ground that understanding. So we have students go through the scaffolded process of what we call guided team design projects. These team design projects begin with sort of a small group, the same group that they're going to make their eventual team design project, final project. But what I'm going to be focusing on are the two projects on the sort of far end of this scaffold of the gecko-inspired adhesive project and the origami robot project, both of which are done within teams and develop a societally relevant design. This hopefully will lead to the ability for students to sort of remove the scaffold and be able to do this on their own in an independent team design project where they look at primary literature, find an inspiration, and use that to make something of societal relevance. Something I want to emphasize is that we're doing this at a pretty large scale. This is a large, R1 university, and it's for 180 students across 36 teams, 40 plus majors, 50% freshmen. So we have a ton of students that we're doing this for, and we truly believe that all of these students, no matter the major, STEM, non-STEM, are capable of doing bio-inspired design. So what do? This first project, called the Gecko-Inspired Adhesive Project, it's awesome. They initially are going to look at the primary literature. I cannot emphasize this enough. We need students in undergraduate STEM courses to be looking at primary literature and understand where knowledge comes from. And so we show them the original biodiscovery, such as this evidence for van der Waals adhesion paper from PNAS, and we ask them to sort of break it down. And I'll talk more about that as we move forward. But essentially, through this process, they create a gecko-inspired adhesive, or green thingy as I call it over here. And this is going to be the development of their skills. When they're doing this, they're building it, they're making it, they're actually using their hands. It's sort of the engineering component of the course, and they're testing it. And we also bring in a gecko. I don't know if anyone's ever felt a gecko's toes. It's the weirdest experience ever because it's sticky, but it's not sticky, and it requires friction for it to be sticky. And so we ask students to feel that and use that as sort of an inspiration to create their own designs. Here, I'll show you a video of students testing their designs. So we want them to test things just like they do in the actual research. So here you have a student causing a frictional force and then testing the measure and detachment angle through this apparatus that we have. And we have them do that over several iterations to see how good is the adhesive, how good is it at sticking. And then, again, we want to connect this to societal relevance. Are they making stuff that matters? And so we task students in their interdisciplinary design teams to make things that are of societal relevance, such as a gecko-inspired adhesive grab bar for the elderly, or a gecko-inspired organ gripper that could be used in robotic surgery. These are the incredibly creative design ideas that students have that they are so capable of, especially within interdisciplinary groups. Another thing students complete is the origami design project, the origami robot design project. In this, they're inspired by this organism. You might be familiar with it. It's disgusting, it's icky, it's crawly, it's all over the place. It's a cockroach. Who would have ever thought that a cockroach could be used for bio-inspiration? Well, because of the primary literature that we see, Cockroaches are incredible at locomotion. They're very robust in their locomotive capacities from getting to point A to point B, going in between crevices, being robust in their overall structure. So what we look at is sort of the inspiration. We use that as inspiration to create something like an origami-based robot that's flexible and bendable and really robust. And we have students do the same thing. Students make the robot, they test it, they analyze it, and they immerse themselves within the bio-inspired design sort of nature of the course. Here's my favorite video of all time of students testing this robot. They're controlling it with their phone here, and they're measuring the gap distance that it can jump between the two tables. Take a look here. This is in slow motion. Clears it. And now they just go, oh. Amazing. It's just so awesome to watch the students as they immerse into this really amazing stuff related to bio-inspired design. So we hope that as they're completing these guided team design projects, they have the capabilities to do their own project. Go into the biological literature, find your own paper on your own, sort of within your teams, and develop a bio-inspired design from start to finish. An example could be like a conch shell-inspired artificial bone. Conch shells have incredible, robust material properties that could be used in a societally relevant context of medical, advancement, medical prosthesis. And we have students then display their work in a sort of design symposium, a conference style like we're at today, so that they can sort of, again, be the researchers, be the scientists that we want them to be. So this is great. The course is fun, it's cool, we do good stuff. But what does it matter unless we can evaluate it and assess it? We have to figure out what are students learning as they're going through this bio-inspired design process. And that's, I think, a really important part of the education side of things here. So in order to do this, we completed the following methods. We used an assessment framework called the 4 building blocks. I don't have the time to explain each of the building blocks. It's explained in the full paper, but I will go over one of the building blocks that's really, really important when it comes to evaluation. We administered a pre-post survey to measure what we call innovation skills. On the program, it said 21st century skills. We changed that to innovation skills. We think that's more accurate. And we used Likert type scale to sort of measure this within students before the course and after the course. We expect before the course their innovation skills are less and they increase after the course. So let's take a look. One of the things that's important about this course is the construct map approach. This is one of the building blocks, and I highly recommend looking into it, specifically the work of Mark Wilson. Here, what we have are skills. Again, innovation skills that we want students to be able to accomplish. We're going to generally call all of these skills here the scientific discovery and translation process, the ability to look at primary literature, translate it, make a design, things like that. This is one of the dimensions that we have. We have 3 overall dimensions that we are calling innovation. And importantly, what I want you to recognize is the ascending competency levels that are here. We have a lower level of required where students just sort of read scientific publications because they're required, or we can go all the way to a higher level of leader where they're translating fundamental principles, they're extracting fundamental principles, they're doing the bio-inspired work that we want them to do. What we expect, we hypothesize as researchers, is this increase as the course goes on. And let's see if we can see that. Let's see if that actually happens based off of some of the analysis that we do. So to sort of ground the context of what students are doing and measuring and sort of looking at the measurement that we do, we ask students to complete something called a discovery decomposition. This is an activity they do constantly. They do this on every single piece of primary literature that they read. We recognize primary literature is tough. It's jargony. I mean, I know for myself, like I struggle sometimes reading methods and education papers, right? So we recognize that and we give them an opportunity to decompose the research through this process called the discovery decomposition. Break it down to its core key components, the 5 main things that this paper talks about. This paper is about how geckos stick. Talk about the bare minimum what you need to know to get the logic flow of the paper. And we connect this back to our survey. We connect this back to what we think students are doing by asking them to answer the following question on a Likert scale. I can extract fundamental principles from scientific publications. Surely, and we hope that when they're doing discovery decompositions over and over and over again, they're getting better and better at extracting fundamental principles because that's what the discovery decomposition is. Another thing students do, something that we call an analogy check. This is a critical part of bio-inspired design, where you look at a design solution from nature, like the gecko, and you try to combat a design problem that we have in society, like hanging things. So here's some student work that I'll show you here. On the left-hand side is the sort of biology, the inspiration, a gecko. How does a gecko work? Its operating environment, function, structure, you name it. And then on the right-hand side is a sort of design idea. I love the names that students come up with for their inventions. So this is Hang and the Gecko. It's reusable wall hangers based off of gecko adhesion. And what I want to focus on is sort of this section. There's a lot here, but I want to focus on how this relates to, again, our assessment, because we have to make sure what students are doing is related to our assessment and our measurement. So what do we see here? Here we see, again, a comparison that's happening between what's in nature and what's designed for society. What you'll notice is that there's actually not all similarities. We don't want to mimic nature. We can do better than nature. We can do better than what's out there because we don't have the constraints that nature has, such as evolution. So instead, what we have is this. And what we hope as students are doing this are they're engaging in this item of I can suggest fundamental principles from scientific publications that could, key part here is translate into novel designs. And that's the main idea that sort of goes with the analogy check. So with this in mind, what I want to emphasize now is, well, what is our research question? Our research question then ends up being, what is the change that we see in the self-reported I skills from pre to post as a result of completing this course? There are two ways I want to show you this, through preliminary results, as I call it, and how those inform something called the item response theory results. I highly recommend looking into item response theory. It changed my world about measurement, about evaluation, about assessment, and I'll show you some references to help you with that. So with the preliminary results, it's pretty straightforward. This is, sort of run-of-the-mill stuff that I think a lot of research does here, where we have items shown on the x-axis here, and on the y-axis a mean Likert rating. What do we notice? We noticed increases pre and post in all of the items that are measuring this dimension of the construct. Same thing in the next dimension that we call interdisciplinary thinking. All of the items show increases, cool. Same thing in this last dimension called interdisciplinary collaboration, increases across all. That's not enough to me. Okay, I don't think that's enough. And so, when we have all of this results that show that agreeability is increasing and there's growth in each dimension, I think we can do better. And that's what I mean by this is not enough. And I would argue that a lot of undergraduate STEM education research stops here. It sort of, averages Likert scales, averages some of the, raw scores the student have, and then sees pre to post increases, and we're good. I think we can go much better with item response theory or item response modeling. So the IRT results, I won't go into the details here because you could take a whole course on it, but basically I want to explain why IRT is awesome. IRT is awesome because it's a scientific approach to measurement. It's a model-based measurement, specifically the Roche model for my analysis at least, where I'm testing a hypothesis. The construct that I showed you before, from required to leader, that's what I think students are going to change into. That's what I think maps onto what students are doing. Is that true? I don't know. Well, that's what we mean by IRT and testing the hypothesis, because we are building the measurement scale and checking whether the data fits the model. That's the scientific approach to measurement that's here. And I think it's more statistically appropriate to do this because one of the things that we do very haphazardly is average Likert scale data. Likert scale data is ordinal. And with statistics... Recording in progress. With statistics, you cannot take ordinal data and turn it into interval raw scores. And you can actually do that within IRT, which is pretty awesome. You can do that in a more appropriate way, I should say. Simply put, when students are completing a Likert survey, the more positive responses are going to yield strongly agree. They're going to map to higher levels of the construct, and then from there, you'll have higher person ability or higher student ability based off of their responses there. I'll show you the IRT results real quick here. We have a right map. Right maps are notoriously confusing. The first thing you think of when you look at this is, why is it this way, vertical? This is a convention within the literature, but I want you to just notice is the overlay that I have here. In the red, we have the pre, in the green, we have the post. What do we notice? We notice growth, and growth is on the logit scale. I don't have the time to explain what a logit is, but I do have a conversion that should be familiar to many of us. A logit gain in student ability from pre to post is pretty much about a standard deviation of growth. And in education literature, that's really strong. That's a pretty significant amount of growth in one semester for students completing this assessment. This is an effect size of 0.75, if you're familiar with that. Again, this is a relatively large effect size. And if you want to really distill all of this down, it's as if there's a one-step increase in the Likert scale across all items. So a student who was agree before went to strongly agree on any of the items that they chose agree for. So this is great. This is awesome. But sort of to wrap up my talk here, what does it mean for us? What can we do with this? Well, with this type of information, we can use these insights to improve both the course and the assessment. We use design-based research to do this. Design-based research, it's iterative, it's responsive, it's feedback-based. We are education researchers, right? But we're also designers. We can go back and figure out ways to improve the course, improve the assessment through assessment redesign. One of the ways to do this is to stop using Likert items, actually, and use something called a Gutman item. I'll show you really briefly what it means. So here's a typical Likert item. The problem with Likert items is that there's a lot of ambiguity between what strongly disagree means to me versus what it means to you. And the distance between strongly disagree and disagree for me and you and anyone who takes a Likert scale score. So why don't we make it a little less ambiguous by turning it into what's called a Gutman scale item that matches with the construct. It actually has levels for each of these responses that matches with the construct that it then gives us a model-based approach to this type of measurement. And I think that's a really strong way to do it. You can see option choice A here just says I can read. Option choice E here says I can translate fundamental principles. So just to finish up here, I know I'm over time here, one last thing that we want to do is analyze and code student work. We ask students sometimes to complete this type of a midterm assessment where they're situated as a researcher, they're situated as a learner within this environment here. And so we want to map actual work rather than self-reported data and map that back to the construct. Again, the construct ends up being a critical part here, and we can use IRT and item response modeling to help us map it appropriately. So overall, I just want to emphasize the following. Bioinspired design is awesome. It's cool. It's a great sort of phenomenon to ground this type of research. Evaluation assessment is critical. We have to measure what students are learning and then go back, use the information, use the insights from there to advance the course and advance the assessment. So I'll stop there. Thank you. Sorry for going a little bit over here. You can connect with me on LinkedIn, and you have the full presentation with that QR code and the full paper on the right-hand side there. Thank you.